In this update on my 386DX build, I thought I would talk through some of the current work I've done since the last video and just some of the challenges or some of the work I now have ahead of me based on what I'm learning. So in the last video, I made it through this to-do list that I've started up on my blog site just to kind of keep some order in which I'm going to work through things, I guess, or try to work through things. And the first 7 steps I had talked through in that last video. So in this video, I'm going to continue, and I've kind of made it down through what I'm looking at as step 15 here. So in the last video, I installed these 2 PAL chips. I got the basic programming on those based on Intel's reference guide for that. And then I have come in now and added additional logic to my PSoC, and so I've got one PSoC in the system that's handling things like clock and A0, A1, S0, S1, etc. And then I've also installed a secondary PSoC that will manage the address decode or just general glue logic for my system beyond what that first PSoC is doing. I've installed latches and transceivers, debug headers. I have connected up my Arduino-based debugger so that I can log some of this to my PC and kind of see what addresses is the system trying to read and write to as far as data at different addresses. And I have installed a pair of flash memory chips to at least get some BIOS type of code that it can read and maybe try to start processing and to see if I can get that to work. So here is an image of my board that I'm using as I go through this. And what I am working on again are these PSoCs. So this left PSoC is the one I had installed in the last video. And at that point, just basic things like clock, could I get the clock going? And I've made some updates to that, and I'll show you that here shortly, along with some logic to generate these other signals, A0, A1, S0, S1, etc. And then I've physically installed the upper, what I'm calling PSoC number 2 for decode, and that is in place along with some initial programming to that, which I will show you. And then I've come in and I've installed address latches, I've installed a control latch off to the left, and data transceivers. So coming out of my processor, the addresses will actually get latched into those 4 ICs that you see up top, U6, 8, 12, and 17. And then off to the right, I have data transceivers. So when I'm sending things out from what I'm calling the internal 386 data bus to the ISA bus, for example, outside of those data transceivers, or bringing it back in. And the control latch off to the left is just latching certain control signals that I might be using as I move forward. I've added in these pin headers just so that I can connect up, whether it's a debugger or just oscilloscope, and look at things easily through those different pins. And in this video, I'm really just actually tapping into the control header at this point to get to my debugger. All of the other signals for address and data that I need for debugging for now, I'm going to actually pull from the ISA bus. And then here is the pair of flash memory chips that I'm using. So I have a pair of ZIF sockets, and each of those just has a small flash memory chip that I am using to program a basic sequence to get started with. And I did populate one of the ISA slots, again, just to plug in this little debugger that I'm using to troubleshoot the system as I go. And so some of the signals I've had to work on in the hardware reference guide from Intel for the 386, they do have a table that shows some of these signals that the 8386 does have, BE3, 2, 1, and 0. And from those, you can generate these signals, because these are not signals off to the right coming from that processor. So an A1, a BHE, and a BLE. BLE is comparable to a 0. Well, I need those signals for my ISA bus or for other things I'm using on the system, maybe for my flash memory, IO, whatever it might be. So I need to generate these. So I've had to put in logic to generate from these 4 inputs, these 3 outputs. I've also needed this S0 and S1, these pair of signals, which help me just kind of understand what bus state I'm in. But to get to these signals, I also had to have certain wait state information generated and also a ready signal. And so out of that same hardware reference guide, I did take a look at, this set of information that's provided. And the stuff up top is pretty straightforward. It's laid out for you. But then down below, they just have this white box, empty box showing another 16R8. That's one of these PAL chips. And aren't real clear as far as what code needs to go into that. But as I've been reading through that manual a little bit more, I have found some snippets that talk about how to generate the ready. I think I have enough information to understand how to generate WS2. And I'm going to guess as I get into this, it's incomplete or I don't have it quite right. And that's all part of the debugging and just analysis that I need to do as I go forward. So here is what I have going into the first PSoC on my system. And so in this PSoC, this isn't organized real well. I'm just kind of throwing stuff down into this tool that lets me program my PSoC. So at some point I'll clean this up and split things out into separate sheets. But this is what I've got so far. So walking just through some of this real quick. What you're going to see up here is I'm generating a clock in the PSoC itself. So this is the PSoC I'm talking about, is this one here, which I just labeled it with a number 1 here on the board. This one's labeled a number 2. And so on this PSoC, I am generating a 50 Hertz clock 2. That's the fastest clock on an 8386 DX system, kind of a system clock. Back in my 286, this would have been just clock. But then I have a half speed of that, which is CLK. So I have a CLK2, I have a CLK. The processor internally is going to run with this CLK. And in my 286 build, that would have been either the peripheral clock, P clock, or just internally within the processor, as it took CLK2 and cut it in half internally. So as I'm bouncing between 286 and 386 DX, I have to kind of, in my mind, keep clear which clock name is really what speed. But for the 386 DX, clock 2 is the kind of the system speed, the fastest speed. The CLK is what the processor is going to run at internally. And then there's also a P clock, or a peripheral clock. And so each of these steps in half. So I've got clock 2 is the fastest, half of that is clock, half of that again is P clock. And I put a note over here to the right. And that's the best I can discern from the documentation I've been reading, is those are the 3 clocks. And those different clocks are used in different places in my logic. And so anytime you see off to the right or somewhere where you see a square box, and it's, I'm sure, very difficult to read here. I can zoom in a little bit, but it'll show what pin I'm connecting to on top of my PSoC. So this is pin 2.3, and I'm going to send out this P clock signal out of 2.3. Versus up here, I'm going to send clock out of 1.6, and I'm going to send clock 2 out of 1.7. And where that's going to come into play is if I do flip over to my schematic here, you'll see that as I get into this PSoC down here, those pins are labeled. So here is my 1.7 for clock 2, 1.6 for clock. Later I might have one that I specifically use to connect to a VIA. And then down here is my 2.3, which is P clock. So those are the pins coming out of this PSoC here. So that's the clock. You know, the reset is pretty simple. I'm taking in an active low reset and sending out an active high reset. And then here's where I have a LUT that's basically taking in all those BEs and creating these output signals here for BLE, BHE, and A1. And just, if you've not caught it in my other videos, anytime I end with a B, that typically means this is an active low, B for bar. But in this case, then I can see I've got pins 1.2, 1.1, and 1.0, which are going to send out my A1, BLE, and BHE. And if I go back into that, I can actually open up and take a look at what is in this. And let me flip over to that program here real quickly. So this is the actual tool I'm using, and so this comes from the vendor for these PSoCs, and in this case this is a little tool they have called PSoC Creator, and I'm using version 4.4. But I can come into this LUT and just look at what is the logic. So basically I'm just looking at those 4 signals and setting up this truth table to say which signals over here should be set, how. And that I am taking off of the documentation that I found in the hardware reference guide. So hopefully that is sitting okay. And I probably need to, now as I look at this, and need to double check that this clock needs to be on clock 2 and not clock, but right now I've got it on clock 2. Then I come over here to the right and I need to generate this S0 and S1, and I've tried to take the logic that I had found. If I back up a slide, this logic here along with this wait state logic down here, and try to implement that here. So what you're seeing down here is I'm generating these wait states. Again, doing my best to look at the code that they've provided, which isn't laid out perfectly clear, but as the more I read it, the more it makes sense. So I'm trying to work through that. And some of you that maybe have done this might have call outs here of things that aren't right, but this is, again, what I have so far. So I have some logic in here that's trying to generate these wait states. I don't have super high confidence that I have this all working quite right yet. So more to come on that, but I am trying to work through the logic for wait state 1, wait state 2, feeding that into this overall schematic or structure that I'm setting up on PSoC number 1 to get to S0 and S1, which I'm then sending out of these pins 12.0 and 12.1. So then with that gave me my 3 clocks. It gave me all of these other outputs. So I have all of these outputs now coming out of this PSoC number 1. Then as far as PSoC number 2, that is just my general address decoding. I'm starting really simple just with something like this, which is essentially a copy over from my 286 build. And so all I'm generating for now are signals for the ROM output and then the RAM output or RAM write, and just basing that very simply off of a few addresses that are good enough for now, at least, to get me going. And this little address decode table is just what I copied over because that's where this is sitting addressing wise currently, but I think that's probably going to change as I continue to work through the design for this 386DX. And so then that gets me to something current state that looks like this. I've got PSoC 1, PSoC 2, and you can see what I have connected where. And I'm not using all of these pins yet by any means, but in time I probably will be. Like all of these bus address lines coming into PSoC number 2, I'm only using some of them. And maybe down the road I can take some of those out. I'm hoping I don't need all of those address lines coming into that PSoC. I'd like to free up some pins to do other things. For example, something that I don't have or hadn't had in here previously was bringing in a clock. And so I still would like to bring in a clock on this, and I have modified it. I am now bringing in a clock up here on this pin 3.2. The only problem with these PSoCs on some of these pins is they have capacitors put on them, and I think it's for sensing type of applications, like touch type applications you might build, which I'm not doing. But any of these, like this one here, these 3, and these 3 that I'm not using, all have capacitors put on them, and at high speed then that will mess with signals, so they're not good GPIO type of pins. So I have for now at least brought in a clock signal into 3.2, even though it's not shown here, and I'm not quite using it yet, but I might be using it in the future, and that'll work fine until I get up to higher speeds, and then I'll have issues. And so that means I do want to free up some other pins to be able to bring in a clock or do other things. Something else, since the last video, I did change out the processor. So in the last video, I had an Intel 386DX processor down here. If you're also watching my 286 series, I've been working on this 286 to 386SX upgrade. And through that, I've learned that the 386SX is different than an SXL processor. And the L processor is the version that supports a true static operation where I can pause the clock and resume the clock or run at any clock speed. And I'm waiting for I have ordered up a 280 or 386 SXL processor, and as soon as that comes in, I'll go back and start trying to get that upgrade working again on my 286. But from that learning, I knew that the 386DX probably was not going to get the job done for my initial debugging, because I want to debug and pause the clock and slow things down. So I did pick up a 386 DXL. And so this is an AMD 386DX/DXL33, and it's upside down here the way I've mounted this, but this is that DXL chip. So I should be able to step through this clockwise at any speed and debug it and be okay. So if I pause there then and maybe flip over, I can pull up this teraterm. So just looking at the output. And if you take a look at my system right now, let me just kind of recap this again. So got the two PSoCs I've been talking about. I've got these PAL chips, got a control latch. I put another control latch in just for expansion, and I was doing some testing, latching some stuff that didn't work out, so I'm not using that yet. And then again, I have all my address latches, I have my data transceivers, I have my pin headers, processor, and then my two flash chips. ISA slot and my ISA connector just to get my signals over to my debug board here. And as a reminder, I'm just doing a shifting in of all of these into a series of pins on the Arduino so that I can come in here and really read all the values on this bus along with some of the control signals. That you can see all of these lines coming over here for different control signals, whether those are clock signals like this one right here. This is my clock signal, and then I've got all these other signals that I'm gonna log and show as I'm trying to debug the system. And then for power, I just tapped this debug board in. There's a little power cable, and I just plugged it in right down here. So it's just pulling off of a pin header, which is sufficient for now. But I'm gonna go ahead and turn on the system, and I'm gonna let this run just for a little bit, and then I'm gonna just stop the serial capture here, and that's good enough. So I'm going to go to the top of this, and what you'll see is, when I turn on the system, I just have a lot of garbage, but eventually I'm trying to get down to where I have read an address of FFFF0. And so right here you can see the processor is sending out a request to read from FFFF0, and that works fine. And it reads a 00EA FFC0 FFFF. And if I go, I can pull up. This is my, well, two things. Let me back up. If I look at the code that I put on these chips, these flash memory chips, basically very simple. I'm gonna, at the very end of this, have a starting point, and this set of flash memory will show up in my mapped memory as FFFF0, not 3, but this is going to be an FFFF0. And when the 386DX starts up, it tries to go to that address and read what should it do. And the very first thing I tell it to do is to do a jump, and to jump to, and I give it a segment of C000 with an offset of 0. So in other words, jump to the physical address of C0000. And that should take me then up to this top. And in that, I'm going to disable interrupts and then call this basic test loop. And that test loop is just going to do this loop you see here. And all it's going to do is use an out. So it's going to do an IO, send out 0, and then it's going to increment it and send out a 1, a 2, a 3, a 4, etc. So that's my basic test just to get something working. So then here what I'm seeing is that I'm going to go ahead and do a jump, and I'm going to jump to that C00000. So this is the code I'm looking for, that if that works, then I should expect the processor to get up to the top of this and start reading and trying to execute this code up here. And what you'll see over here is that as it started up, the processor is looking for the proper address, which is great. And it read as 00EA. So if I again go back down to the bottom of this, and I flip back over here, 00EA. So it read the MSB, LSB. So that looks good. So it read the 00EA. But then it turned around and it read an FFC0. So it got all the way over here. It somehow skipped this. So it read a pair of bytes, it skipped a pair of bytes, and then it read the next pair of bytes. And that makes sense actually as I come back and look at this. It's reading the right data, it's just going at addresses a little bit differently than what my 286 would have done. So it starts at FFF0, but then instead of going to FFF2, 2 bytes later, it goes to 4 bytes later, which makes sense if I'm on a 32-bit processor. And then it read 4 bytes after that, 4 bytes after that. And that meant that it's reading the incorrect information for where it should be jumping to. And then down here, when it does a jump, it's getting to the wrong address. So it's not jumping to the address I expect it to get to. So then the question is, how do I get this to read and jump 2 bytes at a time instead of 4 bytes at a time, if I can do that? Because it seems like in the reference guide, the reference architecture I was looking at, they have 4 separate bytes for RAM, but they're only using 2 ROM chips, so 2 bytes of ROM. But if it's reading 4, expecting 4, that's a problem. Now what I did find is that there is a signal here that I can use going into the processor. It's this BS16, and it says if I assert that, in other words, I pull that signal low, then it's going to do a 16-bit interface instead of a 32-bit interface to access whatever it is that I'm trying to access. So in my case, I'm thinking that if my ROM is enabled for output, maybe I can have BS16 be low at the same time. So in other words, I'll pull the ROM and the BS16 low when I want to read from the ROM, and will that do the job? And this is saying that I have to have the signal set at a certain point in time. And so if I want to use only the lower 16 bits of data, I have to generate this BS16 signal for 16-bit access. And then it just says that when the 386 processor samples that input, it automatically performs any extra bus cycles necessary to complete a transfer on a 16-bit bus. And so that's something I've got to figure out. If I go over to my processor in my schematic, this version of this board that you see here, when I come out of into the processor for BS16, I simply had it go to this pin header. One thought is could I just have that tied to ROM output enable, so when I am telling the ROM to output that goes low, that I'm also going to tell it to do a 16-bit transfer. And that's not the right logic, but maybe that's something I could try just for testing, and I did that. And maybe another thing I can do is take this and just take it to ground and just say that everything is going to be done in a 16-bit fashion. And so let me get this plugged in here. And with that plugged in, I'm going to go back in and let me get to the end of this and reset my system again. So I'm going to go ahead and reconnect my terminal here, and I'm going to hit reset and just let this go by. Okay, so there I get to, that's far enough. So I'm going to go ahead and come back up. So I've got my FFF0, but now it goes to 2 to 6. And I can see it's reading the EA and then the zeros and then this FFC0. So that's all looking better. And if I go back again and pull up, what does this look like? I should be getting a 00 EA, got that. And then I should be getting a 0000, got that. And then I now want an FFC0, and I got that. And then interestingly enough, if I keep going down, and I might not have let this run long enough, so let me do this. I'm going to go ahead and get this going again. And just to get clutter out of the way, I'm going to go ahead and clear the buffer and turn the system back on. Okay, so there it's doing my initial read, and okay, good enough. So I'm going to go ahead and scroll back up here. Okay, so here we have the FFFF0. I see it reads the 3 values that I'm looking for. That looks great. And then I notice that it is jumping, and it is now getting down to C0000. There's this C right before it. There's an address at C0002. I'm going to assume that's a timing thing because I actually don't read the ROM until it looks like here. But I'm at the address of C0000. So it did make the jump down to that correctly. But then at this point, it's reading 4 bytes at a time instead of 2 bytes. And so I still have stuff to figure out of how to work with this signal. The other option that I have is just to get 2 more of these flash memory chips in for the upper word of that 4-byte data values. And that's, I think, what I ultimately would like to do. Now, if I was going to just simply have ROMs and load all programming into RAM and run from RAM, then I'm not worried about it. But there's a performance penalty that if I'm going to have just a pair here instead of 4 flash ROMs, there is a performance penalty that goes with that compared to having the 4 flash ROMs. So I might add a board here with 2 additional flash ROMs and get all of that wired in. You know, I can tap into my data lines here. I can tap into the address lines. It'd be the same address lines already going here. It's just I now need to get into the other 2 bytes of data. And then I think it would read 4 bytes at a time. And so that's something I'm going to experiment with. I need to figure out, how do I best work with this signal, this BS16 signal. And if I go back to the data sheet, let's see if I can get that pulled up here. Or not the data sheet, this is the actual hardware reference manual for this specific chip. And I can search for this BS16, and there is a comment in here about when. Okay, so here's the comment that says if BS16 is asserted during the last clock of a bus cycle, then the processor performs a 16-bit bus cycle. So that's what I've got to get figured out is just timing-wise and going back to my PSoCs. So if I'm already sending out the ROM, maybe I can have another output that sends out this BS16 and then figure out the timing. And that means I'm going to have to get clock or other information coming into this PSoC and trying to figure out where this BS16 needs to properly be signaled. One of 2 options. I'll have to figure out which one is the right one. I think for me, long term, I probably want to support 4 flash ROM chips. So that maybe is what I'm going to try to do next, is just add a quick daughter board, get 2 additional ZIF sockets, and get ready to go with 4. That also means that when I go out and I build my ROM right now, when I do a build, I have a little utility that splits the ROM in 2. So I build it or assemble it, and then I split it, and this utility takes a single assembled file and splits it across the 2 ROMs. I'll have to make a version of that splits across 4. So I think the work I've got ahead of me is to add 2 more ZIF sockets on a daughter board and get that wired in, update my split utility to be able to split an assembled ROM file into 4 ROMs, and then get that back in, not leverage this BS16 signal for now, and see if I can properly be reading that. And then when I get to the RAM, I have my 4 separate, so I'll be good to go there. And then I'll have stuff to figure out later when I do I/O. Do I have issues at that point or not? Or is there something I need to do with the BS16 when it comes to working with I/O or other things on the 16-bit bus? So a whole bunch for me to figure out there, but that's what I'm seeing on my output, is that I can now get 2 starting up my 386 DXL. I am getting to the correct location on the flash memory. I am reading where to jump to. I do the jump. I'm getting to that location. And then at that point, it's reading a C031. And if I go over to look at the top of my ROM, C031 is what I would expect. So it's working. I am starting up processor. I'm reading, I'm jumping, I'm reading. But then at that point, I'm jumping, well, not jumping, but I'm reading too much at a time. So I'll have to work on that. And that's where I want to stop this video. So that's what I'm learning so far. So far, I think things are going pretty well. It tells me that my PAL, that code that I put on the PAL, is quasi-correct at least. It seems to be working so far. The stuff that I have on my two PSoCs is good enough to get me this far. So the next steps then might be to get my additional ZIFs in here. I'll probably have some additional cleanup code on the PSoC logic, both of these. And I'm probably going to go back and just double check that everything I had on the PALs is correct as far as code. So good enough for now. I think on my 286 series, I should hopefully have in a 386 SXL pretty soon. And then I'll get back over to that, trying to get that upgrade working on that system.